Let's do an example of the Gibbs-Thompson equation. So we run a DSC and we notice that on our DSC the melting points and the freezing points are offset by about 10 degrees C. So the question is, what was the radius of those decane particles? So let's write down the Gibbs-Thompson equation. We see delta T, how much the freezing point is depressed by, is a function of the original melting point twice the surface energy, the molar volume of the solid, the radius of the solid particles initially formed, and the heat of fusion. So we're going to have to look up several parameters. We can find the heat of fusion, and we need also the molar volume, and that's not usually tabulated, but what we can do is just find the molar mass and divide that by the density. So we're going to have to look up the density. Of course, we can calculate the molar mass. And the surface energy for solid decane is not available, so we'll use something equivalent, polyethylene, since they're both simple hydrocarbons. So polyethylene is 35 millinewtons per meter. Okay, so now we're ready to solve the problem. We don't have the density for solid decane, but it will be a little bit higher than liquid decane, so we'll approximate it as 750 kilograms per meter cubed, and the molar mass okay, so we plug in our molar mass of 142 kilograms per mole. We plug in our density of 750 kilograms per meter cubed, and we get our molar volume for the solid of 1.9 times 10 negative 4 meters cubed per mole. Plug that in over here. We've got our temperature, our normal melting temperature, our surface energy. We've converted it from millijoules per meter squared to joules per meter squared. Our delta T and our delta H, which we converted from kilojoules to joules. Okay, so we're ready to plug all that in. And we end up with 11 nanometers. And if we think about the size of a decane molecule, it's about 1 nanometer long or so. And so this is getting pretty small. This is getting down almost to molecular dimensions. And so this is quite a big supercooling effect.